again, I'm sorry for not being able to record these videos as often as I need to. But now I have sort of time and aloneness to record this video. So we're going to go back to relationship theory, and we're going to go back to the concept of relationships as topological space. So now I want to introduce relationships as topological spaces. So what I want to lead to in this lecture, just get the lighting correctly. What I want to lead to in this lecture is the graph homology. And of course, it always wraps back to homology. Graph homotopies are much more complex, but today we're going to be focusing on the graph homology. So, to begin, recall that every relationship, be it a monogamous relationship or a polyamorous relationship, can be interpreted as graphs, directed or undirected graphs. Is that seen? I hope that's seen. Okay, so just lower that a bit more so you guys can see better. So, because we can interpret relationships as graphs, we can in turn interpret the graphs as topological spaces. So, given a graph gamma, we interpret gamma as a topological space. And because this is a topological space, it can be classified by homotopy and homology that comes intrinsically for a topological space X. So X, a topological space. A manifold or algebraic variety. So any kind of notion that is similar to a topological space, we can classify X. X can be classified via homology. So, what I want to lead to is classifying relationships through homology. So the goal, so what I want you guys to learn in this video is to classify relationships using the tool or the power of homology. So to begin, we're going to revisit the concept of a graph. So, let's revisit the concept of a graph. Last video, I believe, was about graph invariance, right? So, matrix invariance of graphs, if I'm not mistaken. So, we're going to go back to the formal definition of a graph. So, a graph, gamma, is a set of nodes x1 through xn, such that there exists a set of maps a1 through an, such that each of these ai maps some x I or x alpha in gamma to another x beta in gamma. So each AI is my edge set maps my vertices, right? So for example, for this relation over here, maps x to y, B that maps y to z, and C that maps z to x. So that's how I want to that's how I want to represent them for the purposes of this lecture. So before I actually get into homologies, I must first start with an example, of course. So an example computation before we get to the formulas or the general formulas for the homology of a given relationship. So first, I want to consider a relationship between three people, but it's a bit more complicated. So I still have the same people x, y, and z, but it goes this way. So it's x to this is y, and this is z. So x to y, y to z, z to x. And then this is a, b, c, and I have another map with z, x, another edge. I'll call it d. Okay. So so what you guys will observe from this graph or this relationship is that there are three cycles, and by cycles I mean paths that loop around. So the first one is this one over here, so namely x to y to z, respectively mapped z to x. So respectively a, b, and c. So I will denote this edge over here as simply a plus b plus c. Okay? So it's a denotation. I'm combining the maps so that I start at x, travel along a to y, travel along b to z, and travel along c to go back to x. So that's what it means by a plus b plus c. Okay? The next cycle is if I travel along a, b, and d. Okay? So I can go along this outer part or outer region. So it will look like x to y to z, back to x. However, this time I'm traveling along a, b, and then d. So I'm going to denote this as a plus b plus d. Okay? So now there's another path here. There are three paths in fact. This one over here is c minus d. So I travel along c and I backtrack through d. Okay? So it takes me from x, from c, x, then back to z. This is c and then d. And since I'm traveling converse to the direction of d, I'm going to be denoting as a minus direction. So it would be c minus d. It's my third cycle. So a plus b plus c, a plus b plus d, and c minus d are my cycles. And the term cycles is starting to become familiar because, as you recall from homology, cycles is involved cycles, mod, boundaries, remember? So you guys will see in a second why exactly we chose this terminology. So if I combine a, b, and c minus d, I will precisely get a plus b plus d. So I'll just unpack it here. A plus b plus c plus c minus d gives me a plus b plus d. You guys can check it first. I'll leave it as an exercise for you guys to verify this relation. Okay. So actually, this is done by a special procedure which I will give you guys as an exercise. So to construct a homology, we will first consider the exact sequence, right? It's an exact sequence of C, so dot dot dot, C2, So, or really it's just 0. We're just going to consider this part of an exact sequence. C1 and C0. Okay. So, what's my C0? So, recall that from homology, C0 is the free abelian group over generators that generate simplices of dimension 0, so points. And in this case, it's our nodes, right? So, there are precisely 3 nodes, and therefore there will be 3 generators for a free abelian group. So, I'm just going to say that C0 is exactly, or denoted by the free abelian group of the generators X, Y, Z. Now this free abelian group would then be sort of isomorphic, but I wouldn't say exactly isomorphic on the nodes with C3. I'll just say the free abelian group on X, Y, Z, right? And then my C1 would then be supposedly the free abelian group generated by the number or the exactly all of the edges, or in this case, or in the simplicial complex case, would be one-dimensional simplices, so edges. So it would be the free abelian group. So I would denote C1 as the free abelian group, define C1 as the free abelian group over my edges, which is A, B, C, and D. Okay? So, but then, so of course, now since we have an exact sequence, of course there will be certain boundary operators. So like del, so del 1 and del 0. So del 1. I only want to consider del 1 right now. Yep. Oh, del 1 and del 2. So, yeah, there's that. Now my C2 would simply be the free abelian group on really nothing. It's just trivial. It's the trivial group. The trivial group. This is simply the trivial group because we didn't really explicitly say that there is a two-dimensional simplex attached to this graph. So it's just a trivial group. That's my C2. Or rather, this is the image of the, sorry. That's really all we need to know about the data required to complete homology, the first homology of my topology space. Now, what we need next, we need the kernel of our del 1. So how do we find it? First, we need to find the boundaries, right? So let's first find what exactly del 1 is by finding out what exactly does it happen. So it's a boundary operator, so therefore it's logical to assume that it maps each of these edges to their boundaries, and we call it that the boundary of an edge is simply its endpoints. So you guys can find out that the del 1 of A, the edge A, is simply the two edges it traverses across. So y minus x. It's a linear combination of the 2 points called from our February theory. So del 1 of B, then B, C minus Y, and del 1 of C would then be X minus C. And my del 1 of B would also be X minus C, which is it's the same as del of C. So there's my images, and because I have these, of course I have this map here, it's already defined. So similarly, my del 1 would map elements, so cycles, the 0 group. So what I mean by cycles to the 0 group is it maps each of these cycles to the identity of the next group, well, not 0 group, but the identity of the next group. So the identity of C1 Because any kind of image, so the image of my cycles is precisely the zero or the identity of C1. Okay, so because there are really no boundaries for each of these cycles. Because these cycles, although two-dimensional in nature, are really just lines. So there are no boundaries that encompass them. If I attach some sort of simplex over here, perhaps I can find the boundary and then I can map it. But for now, since there are really no other cells attached to this this graph, then this is it. This is all we have. It's only going to run up to C2. If you want to complete higher homology groups such as H2, H3, it's all going to vanish. Right? So the only important homology groups for us is really C0 and C1. So, because we have these relationships over here and we're in this exact sequence, it must hold that del1 extends to some homomorphism between C1 and C0. And likewise, C del2 extends to some homomorphism between C2 and C1. And you guys can check that the homomorphism satisfies this property. So the property is that the del1 of A plus B plus C is precisely equal to the del1 of A plus the del1 of B plus the del1 of C. And that's it. And that will also equal 0. Now, if I want to consider cycles in C1, my del1 would map any cycle in C1 to identity as well of C0. So, because we've said this, the kernel of del1 is precisely the free abelian group on the two cycles. Yeah, okay. The free abelian group on the two cycles over here. The reason why I'm not going to consider C minus D is because through this formula over here, C minus D is a linear combination of A plus B plus C and A plus B plus D. So this is part of the entire space generated by these two. So I can consider that as a generator of a free abelian group. Because when we're trying to construct free abelian group generators, we only consider the most fundamental elements in that group. So my free abelian group on A plus B plus C and A plus B plus D. That's all I'm considering. So now that I have my kernel here as del1, you'll notice that this free abelian group on two generators is precisely isomorphic. It's actually isomorphic. A plus B plus C, A plus B plus D is isomorphic to integers, two-dimensional integer C. Because two-dimensional integer C2 is a free abelian group on two generators XY. And I was wrong when I said this is isomorphic. This is actually isomorphic to Z3. And this one to Z4. But that doesn't mean anything in our computations. Okay. So now that I have my kernel of del1 and my image of del2, then I can finally construct my homology group. So my first homology group, so isomorphic to Z2. And so the first homology group of my space or my relationship is exactly Z2. And it lends itself to the fact that we have two holes inside our relationship. And that's why it's Z2. Now, if there's going to be an additional edge over here, you would say that's Z3. And if I add another one, Z4, so on and so forth. So, in general, the first homology group for a certain relationship will be given by this formula. In general. General, so consider a gamma that is arbitrary, so arbitrary gamma that is of one half function. So, and I will consider the spanning tree of F, of gamma, which is T. So this is the spanning tree of gamma. So, with T, the spanning tree. Then the first homology group of gamma, when interpreted as a topological space, is isomorphic, or it's exactly the free abelian group of the generators of the edge set minus the spanning tree of my gamma, so edge. And this is isomorphic to the direct sum over the elements in my edge set minus the elements in my vertex set plus plus 1. So instead of having to compute the spanning tree every time and then minusing or removing the elements or removing those elements in the spanning tree from my edge set and then laying it all out, you can just use the fact that the number of elements inside my edge set minus the spanning tree is precisely equal to the number of elements in my edge set minus the number of elements in my vertex set plus 1. So, for example, I have a graph or I have a relationship gamma. So, I have a relationship graph gamma with, let's say, 2 edges and 2 people. So, it will look like this. What is this first homology group? Then we consider the amount of people inside. So 1 and then 2. And then there's precisely 1 edge. So the edge set is simply just this edge connecting 1 to 2. Now, let's consider the case 1. So I have 3 people. This relationship dynamic. How many edges are there? It's precisely 1, 2, 3, 4 edges and 3 people. So my vertex set is precisely of cardinality 3, and my edge set is of cardinality 4. So 4 minus 3 plus 1. This is 4 minus 3 plus 1 is exactly 2. So it will be the direct sum of z up to 2 copies. So it will be z direct sum of z, which is isomorphic to z2. What is that? So how about disconnected relationship? So instead of just one big polyamorous relationship, I want to consider 2 relationships as one. But there is probably some cases or some people in those relationships that don't like each other, for example. So what is that? What is the formula for that? So for that case. So this time we have. So a while ago we had the set of people E, and then we had the set of this is a set of edges or relationships E, the set of people V, and we have the spanning tree E. Now we consider the set of connected components. So this time we have the number of relationships as a whole C, and we consider the amount they have. We don't need P anymore. So for a disconnected, so n path components, or the order of C, or the cardinality of C path components, we don't really need to consider spanning tree anymore, so you can just consider the edge set. Then the first homology of my gamma is exactly isomorphic to the direct sum over E minus B plus C copies of Z. So let's say I have 2 relationships. So the one from 1 to 2 except I'm just going to make it 3. And I have one over here that's a monogamous relationship. And let's say I want to consider both of these as my gamma. Then I have how many edges? I have 1, 2, 3, 4 edges. So the cardinality of my edge set is precisely 4. I have 5 people, so the cardinality of my vertex set is 5. And I have 2 disconnected components, 2 disconnected relationships, so the cardinality of my set C is 2. So then my first homology group of my gamma is isomorphic to the direct sum over E minus 5 plus 2. So that is 4, 5, 2. That is 4, 5, 2. So simply Z. 4 minus 5 plus 2. So that's negative 1 plus 2, which is 1. So over 1 copy of Z, so simply just Z. And that's true because I only have 1 pole over here. There's no holes in this relationship. So this holds. That's true. So how about the zeroth homology group? So the zeroth homology group for any kind of connected, so if my gamma is only of 1/2 component, my zeroth homology group is trivial already, all throughout. But it's different, or no, I mean it's just Z, not the trivial, but rather just Z. This is zeroth homology group of any X, or X only having 1/2 component. But there's a difference. It's a different case whenever my space X has 2 path components. copolinets are two disjoint topological spaces inside them. And likewise, if my relationships are of two distinct or disjoint relationships, my zeroth homology group will likewise change. So the zeroth homology group actually reflects how many path components you have inside your topological space, and I discussed that in family theory. So the amount of path components in your space is precisely the degree of my C, or my homology group. So the zeroth homology group of my relationship of varying amounts of different disjoint relationships is precisely the direct sum over the amount of distinct relationships, of copies of C. That's isomorphic Z to the cardinality of my relationship set. And this relationship set consists of relationships that are disjoint, so not connected at all, albeit they can be connected in their own little worlds. So that sometimes you would consider the reduced homology for some reasons, and that's denoted by H tilde 0 of my gamma, and that's really just this minus 1. So my H0 tilde of my relationship gamma is isomorphic to direct sum over cardinality C minus 1 on Z. So C minus 1 copies of Z direct sum, which is likewise isomorphic to Z to this C minus 1. So using this schema, you guys can classify any kind of relation you want to disjoint or not, or connected or not, using these two or these three formulas. So the formula for the first homology, for the zeroth homology. If you guys want to find higher dimensional homologies for these relationships, then you will have to consider three-dimensional kinds. So you will have to attach two-dimensional and three-dimensional, etc. cells or simplicial complexes, simplices to our spaces, and then compute the relevant or the necessary or the corresponding simplicial homologies. So one tactic that you can do is, given a relationship, you can attach simplices to these such that they become homeomorphic to a known space. So given this kind of relationship, I can attach cells such that it can become some tetrahedron. I can attach two cells onto the remaining spaces so that it becomes something isomorphic to a sphere. Homeomorphic, rather, to a sphere. And because it's homeomorphic to a sphere, its homology group would be the same as the homology group of a sphere. But again, if you want to classify using higher dimensional homologies, you guys need to watch out for what kind of spaces you make your relationships homeomorphic to, because I can attach more cells to something like this relationship and still end up with something homeomorphic to a sphere, which is homeomorphic to this, which breaks our classification schema. So if you guys want to classify with higher dimensional homologies or homologies greater than k equals 1, then be careful on your attaching maps. Okay? So really the classification schema for what I discussed for the purposes of this lecture is really just up to the first homology group. And since there's a good duality between the first homology group and the cohomology group, you can compute the cohomology groups, right, from 0 and 1. that's really it for this lecture. I understand that it's not quite as long as the other lectures, but I hope I got my point across. Classification schemas for relationships get whittled down to various things, such as naming them, but one of the most versatile tools, which graph theorists have used for years, is using homology to classify them. And again, because relationships can be modeled as graphs,